Okay, we're back for part two of lesson 2.2 in the AP Calculus curriculum, defining the derivative function and using derivative notation. So this time we're going to determine the equation of a line tangent to a curve at a given point, and we're going to use the essential knowledge of the derivative function at a point is the slope of the line tangent to the graph of the function at that point. We're going to find the equation, and we're going to use the tangent line of the graph to estimate the derivative at a point. That's what we're going to be doing here today. Let's go see what we can do. All right, so if we're asked to find the equation of a tangent line to a function analytically, so we're given the function in an equation form and asked to find, let's say, find the equation of the tangent line to the function at a given x value. Here we're going to find the equation of the tangent line of the function f of x equals 3x squared plus 2x minus 1 at x equals 5. So we did the limit definition for the derivative at a point the other day. And so we're going to use that. We're going to calculate f of, just like we did in 2.1. Oops, look at this. Draw. So we're going to look and see that f of 5, first off, is 3 times 25 plus 10 minus 1, 75, 85 minus 1, that's 84, right? And recall that yesterday we have f of x plus h minus f of x over h. That looks really, really close to that limit. So we're looking for f prime at 5 so we can find the slope, and that's the limit as h goes to 0 of that difference quotient. And so we're going to plug in 5, which is the limit as h goes to 0 of f of 5 plus h minus f of 5 all over h. And so f of 5 plus h then is going to be, let's see, the limit as h goes to 0 of 3 times 5 squared plus, 5 plus h squared. Plus 2 times 5 plus h minus 1. And then minus, now f of 5 is 3 times 5 squared plus 2 times 5 minus 1. And that's all over h. So when we do this, we're going to do some algebra here. That's going to be 3 times 5 times 5 is 25. 5h plus 5h is 10h. And then plus h squared plus 10 plus 2h minus 1. And then minus 3 times 25 plus 10 minus 1 all over h. It's going to be the limit as h goes to 0. So here we're going to have, let's say it's 10h here. 75 plus 30h and then plus 3h squared plus 10 plus 2h minus 1. And now we're going to subtract 75 minus 10 and plus 1. And that's all over h. And so watch what happens here. Our 75 and our negative 75 cancel, our 10 and our negative 10 cancel, our negative 1 and our 1 cancel. And so now we're left with, I'm going to come up top now and finish this since we ran out of room down here. So this is now going to be equal to the limit as h goes to 0 of 32h, we combine those h's, plus 3h squared over h, which is the limit as h goes to 0 of 32 plus 3h, which equals 32. So at x equals 5, the slope of the tangent line, remember, this is our f prime of 5. So that's the slope of the tangent line. So we can write the tangent line equation as y equals the slope times x minus x1 plus y1. This is called a point slope equation of the line. We plug in x1 and y1 for a point that we know is on the graph, then we can write the equation of this tangent line. So our slope is our f prime of 5, which is 32. We keep the x because we need the variable in the line equation, minus, now x1 is 5. That's the x value of the point 584 that we got from here, and then plus 84. And this is going to be the equation of the line at x equals 5. You might distribute that and simplify to get it in slope-intercept form, but a lot of times they're going to leave it in this form here. But we could also do this as 32x minus 160 plus 84. So that would be 32x minus 76. Either way, that's how you find the equation of a tangent line. You're going to find the point on the graph at that x value. We found the point 584. Then we're going to find the derivative at the x value for the function using the limit definition. Then we're going to use that for the slope of the line. Plug in the point that we found into the slope intercept or slope point slope formula for the line, equation of a line, and that's how we find the equation of our line. We can do this if we're given a table and a graph also. It's a little easier with this one because we don't have to have the limits and stuff, but we know that the equation of the tangent line to a function is going to be, draw the slope times x minus x1 plus y1. The x1, y1, if we're looking at the tangent line to the graph at x equals 1, then the point on the function is going to come from x equals 1 and f of x equals 7. So the point 1, 7 we know is on the graph. All we need to do is find the slope at x equals 1, which is going to be the f prime of 1. So our function, our equation for our tangent line is going to be y equals, that's the f prime at 1, x minus the x value 1 on the point plus the y value. And this is the equation of the tangent line for the function f of x given by this table with the graph, with the tables f prime and f of x. We could also simplify that to write it in slope-intercept form if we needed to, negative 2x plus 2 plus 7 or negative 2x plus 9. And then if we're given the equation of the tangent line and asked to find a value of the function, we can do that as well because we know that the function and the tangent line intersect at that point. If a line is tangent at x equals a, then the point where the two graphs, the graph of the function and the tangent line intersect, is at x equals a. So here we're given an equation of a tangent line to f of x at x equals negative 2 and then asked to find f of negative 2. So that means that f of negative 2 has to be equal to the same y value that you get when you plug in negative 2 to the tangent line at negative 2. So we're just going to plug that in. and get negative 16. And that's how we do that. Now you cannot, under any circumstance, we can only do this because we know this tangent at x equals negative 2. So we cannot say that that line gives us a value for something like f of 0 or f of 3 or even f of negative 3. We can't use those because we don't know anything about what the function does except at x equals negative 2. We know that it has to intersect the line that's tangent at x equals negative 2. And so that's how we're going to use section 2.2, lesson 2.2 in our calculus curriculum.